Hey folks, how you doing today? Hope your Thursday's going well. Let's wind that down over here. Alright, awesome. So we're going to get moving on with trees, and we'll do the more sane binary trees here. Again, sorry for the entry nonsense. I thought it was going to be easier than it was, and then it just made no sense because we hadn't talked about binary trees yet. So, my mistake. I'm sorry. We'll talk about binary trees, and then we'll come back to end trees and make them make a little bit more sense. So the idea with the binary tree is we have these inner nodes here. And the inner nodes have a little bit of information about them. So they need a parent, they have a left child, they have a right child, and they have the data itself. Right, so self-parent is the parent, self.left child is the left child, self.right child is the right child, and self.data is the data. Right? It is, remember, that we just have two connections, right? We're a binary tree. You have a left and a right, and either one of those is optional. Let's pull this up here. So that's the linked nodes that we're going to use to represent these relationships. Right? Each child is another tree itself, right? So it's this recursive behavior. Right? So they have left, they have right, they still have depths, they have heights, that sort of thing. So this is a general binary tree that we looked at on Tuesday. Tuesday was just a wash. I'm sorry, just nonsense. So we'll fix that. Okay. So we have all these values. Great. That's our node, and then our binary tree has an init. Right. That maybe takes some data, and we have root is a node. So root has no parent. Right. So we can default all these here to nones, which is nice. Say, hey, if you don't have a value, we'll assume it's none. And actually, data should come first, because then we can do these nice and positional and that sort of thing. Data. And you probably need some data, right? We'll have the data, and then we have nones. We have no left, no right, no parent. Self.node. Okay, so that's the root of the tree. Right? That's how we make a new binary tree. Easy. Okay, and then we were going to have the, like an add. Now this one we can't just add a child because there's no generic add child. We can add a left data, and we can add right. So we're going to take self.root, right? We're going to set the left child, root's left child, to a new node. So self node, given the data. Now in this case, we are the parent, so self is the parent, right? It has no left and no right, so it's just going to add a left here. Okay, so we can add something to the left, and with this add right's the same thing. We're going to add something to the right. Instead, we'll say our right child is now this thing, where we are the parent. Okay. Again, we can kind of use that positional wrapper too, which is nice. Right? And we can hand them back in position. We'll take our positional wrapper around the node. So this one has a node, is the node. Self.node.data is the data there. Other.node is self.node. Okay. And just fixing this up. So we store a given node here, right, in the position. So we're wrapping a position around the node so they can work with positions. So we can hand them a position, and then they can add stuff to that position. So then we need a make position helper. And right, we have this little define make position helper. Where'd that one go? We have a validate. Here's my little position wrapper. Where's my make position? That was valid. I thought we had a make position. What that position? Okay, we didn't have one. We did our own. That's fine. Let's add a little helper. We'll define a make position helper. So make a position out of a node. Right, how about that? So we're going to return self.position. Right? And position needs the container and the node. So the container is us, and the node is the node. I guess that's probably why we did it as a one-liner, but that's okay. Not too big of a deal. Okay, so maybe we want to do this then. So maybe we make a node. Right, or we can just return self.makePosition out of self.root.leftChild. Sure. So we'll add the left child, return it, and then we'll add the right child, return it. Okay, so you can add left, you can add right, given data. And maybe actually we want to, okay, let's do this better. Let's say we want to add to a given position, right? Because we want to be able to interact with our positions. If you give me a position to add to, we're going to validate it. So let's validate our position. Let's go back and steal this one here, our little validate position. So if it's a position and the container is us, great. If that is, then we can return the positions node. Right? The node is that position. It belongs in our tree. Right? Okay, so if you give me a position, let's validate it here. So let's the position, or I guess that's going to be the node, right? Self.validate position. Make sure it belongs in our tree, and then we'll get the node back out. And then we can take the node's right child. We're adding the data and ourself as the container, right? Oh, now, so the parent now is going to be the node. We're adding that to the node. So validate the position. Now this is going to be add a left child to the node. Right? And then we don't want node here. Oh yeah, we're going to make a new node, and then it's node.leftChild. And this is node.rightChild. Okay, the whole idea here is we want to be able to add stuff to it. So let's clear this out. So if I hand you a position in my binary tree, right? Great. You can add a left child to it, or you can add a right child to it. And we probably want to check, right, that if node.leftChild is not none, raise a, I don't know, value error, left child already exists. Right? You probably can't add something if it's already there. So we'll do a quick little check here. That's a right child. So you can't add to the right if we already have a right, because bad things will happen if we hurt our tree like that. Okay? We probably don't define how do we get our root back out. Return self.makePosition out of self.root is the node. Give them the root position. Okay? We can add left, we can add right. We can get parent, define parent of a given position. Right, so we're going to validate the node, validate the position, we get a node, and then we can return self.makePosition out of node.parent. So I guess we should check if node is none, return none, right? Because if we don't have a parent, right? If our parent is none, like we have no parent, right? Then we shouldn't give them anything. All right. Everyone's confused in chat. That's okay. And we should be able to get a left and get a right. Right, same idea. We'll define a left of a position. We'll return that left child. Validate it, and then return make position of the left child. Right, and right's the same thing, so I can get the right position out. Validate, return the right child. Okay. So let's see if we can work with our binary tree. So we should be able to have our binary tree, the binary tree, and let's add something to it. Say let's add, I don't know, like 10. Okay, and then that's going to be a what do we get back out? That's just a tree, right? That's the tree itself. So now we don't have any positions. So I need to work with the positions to get something out. So we're going to have root is our binary tree dot root. Now that's the root position. So then root is the position that we want to add children to. So we're going to take binary tree, we can call add left or add right, given the root position, and what data do we want to add? All right, what do we want to add to the left of root? Well, I don't know, let's add a 5. Okay, we'll take our binary tree, we'll add right, add to the right of root, and say, I don't know, maybe we'll add a 15. Right? So the idea of what we have here then, we should have 10, we should have 5, we should have 15. Okay, and then we should be able to get a left child is binary tree dot left of the root. Oh, I'm sorry, we can just assign that, right? This is left child. There we go. Because it should return us that value, and this should be the right child. We don't have to ask it, right? It returns those values for us, which is nice. Then if I want to add more things, right, I can take my binary tree. I can say, hey, I want to add right of the left child. And let's say, let's add a 1. I don't know, sure. And our binary tree dot add left, I will add right of the right child. We'll add, say, 100. Okay? So we can get the data out of each of those positions if we want. Right, well, let's just put it in debug mode. Let's see if we can see our tree here. Right? It's this linked object. So each node in the tree has a link to a parent, a link to a left child, and a link to a right child. So let's see what we can see. Oh dear. Did we crash? We had an exception. Node object is not callable. Uh-oh. Binary tree root. Root. Oh, we can't use, yep. Okay, so we can't call it root. So this should be the private root here. Self.root. There we go. Right, we can't have a method with or a function that's the same name as a variable. That's annoying. Okay, I think we're okay there. Right, let's stop, let's try that again. All right, cool. So we got our binary tree, right? It has a node. Oh, it's protected here. That's right. The root here is the root node. Its data is 10. It has a left child. Data is 5, and it has a right child, which data is 15. The left child has a right child, which is 1, and the right child has nothing yet because we haven't added right. So once we add right, let's step into our code. We're going to add to right. We're going to validate the node. We're good. Belongs to the tree. And we got our right child. Okay, so we're good so far. So with this binary tree here, oh, we should be able to figure out height, right? So we want to do the same thing. We had height and depth as well. So let's see. I think we had those over here. Depth and height. Right, so current parent is self parent, and while it's not none, we add one. So it's not self.parent, so it's self.root.parent, right, is the current one. And then the parent's parent, because root is a node, and node has a parent. So we can just keep looking at parents until we find no parent there. So the depth, right? That's the depth of the current tree, right? And then height, then all we need is leaf here. So is leaf, return, I think we want a position here, right? We want to check if a position, yeah. If a position is a leaf here, let's do that. Let's return we need to validate the position first. And then we're going to return node.leftChild is none, and node.rightChild is none. Right? If our left is none and our right is none, we're a leaf. Okay? So then height of a tree, right, goes through each. Needs to go through each position. That's not ideal. Let's see. Yeah. We could just do it. We'll leave out the positions here. Self dot root. Let's try that. Okay, so each tree is a tree here. Let's try that. So see if we can get the height binary tree dot height. Let's run that. Uh-oh. Children. Oh, that's right. Let's see. So we need, because we don't need the max, because we don't have a children list. We just need the left and the right. Let's see. Because we need both in there then. Okay, okay. So we need the height of our children, is the max height of our children. So we just need to look for if they're not none, because we got to check to make sure they're not none. Okay, let's just do children. Let's get the children of the tree here. Children. So if we want to give our children positions, right? We're going to yield the positions of our children. There we go. This is going to work. This will be better. So I can, if, let's see, children of a position, we'll validate the node. Okay, and then we're going to check if node.leftChild is not none. We're going to yield self.makePosition of node.leftChild. And if node.rightChild is not none, we'll do the same thing. We'll yield that one. Right child. Okay, so you can get the children of a position. Right, we'll give you the left, we'll give you the right. So height should be of a given position. Right, height of a position. We'll validate the node. Make sure it belongs in our tree then. And then if that's good, so is leaf, yeah, is leaf going to go off of position as well. We'll validate that one. Node, node. All right, we want depth of a position. So we're going to use position everywhere here because that's how we're going to interact with our tree. Position. Validate the node. The node's parent. Here is the current parent. Okay, so children, we get a node. We make position, we get the height. Start with our node, and no, we don't need the node there, do we? We just need the height, the position. So if it's a leaf, okay, cool. So if it's a leaf of that position, we return depth of that position. If it's not, then we're going to return the max of self.height of the child for each child in self.children of the position. So if you give me a position, calculate the height. If it's a leaf, we'll give you the depth. If it's not a leaf, we're going to go find the max height of each child position there. All right, so let's see if that one still gives us our tree height of, say, root. What's the height of root? So the height from the root position is 2. Right? There's 2 generations underneath it. Great. And we can even check here. We can say, hey, if you don't tell me height here, height position is none. So if position is none, we'll say position is equal to self.root. How about that? So you don't even have to give me the root then. We'll assume it's root unless you tell me otherwise. So then I can say, hey, what's the height of a tree rooted here? Cool. I should be able to calculate depth. So each one should have a depth. Each one should have a height. We can get through. Okay, so we've got the base tree going here. Right, this is the base of the tree. Then we want to figure out, well, how do we get all of the positions out of the tree? Right, how do we iterate over a tree? And now, this is where it's going to make a whole lot more sense, right? So we added some more children here. We said, hey, maybe this was a 1, and maybe this was a 100 or something here. So if I want to iterate over a tree, we've got a couple options, right? Again, depending on what we want to do. So we call them a couple different things. So there's a pre-order, an in-order, and a post-order. So a pre-order is going to do left, center, right. An in-order is going to go center. No, I'm sorry. That's backwards. An in-order is going to go left, center, right, or me. So if you have a left, you go left. If you don't have a left, you process yourself, and then you process the right children. Okay. The pre-order does itself, and then it's left, and then it's right, and the post-order is left, right, and then itself. Maybe it should be S for self. Self. Self, left, right, self, left, right, self. Now again, depending on how we're storing these here is going to matter. So these are just in an unsorted order. We're just throwing items in a tree here just to have some sort of hierarchy here. So they're not in a sorted order. So they're not going to make a whole lot of sense. But we can do a pre-order, we can do an in-order, we can do a post-order. Okay. So let's write those little traversals there. Pop this open. Make sure I'm not going crazy like last time. All right. Excuse me. All right, let's take a look at our binary tree here. Excuse me. All right, where is it here? There we go. There's our traversals here. Okay. So if we want to do a pre-order traversal here, we'll add a little pre-order traversal. To do that, right, the idea with a pre-order is, where's this one here? We talk about pre-orders. So we get the root first, then we get the subroot, and that one visits itself and then does the subroots, and then visits itself, does the subroots. So we get like this one first, and then we get its left, which does, again, a recursive pre-order, which gives itself, and its left and its right, on and on and on and on. We're going to check each item exhaustively first. So our pre-order then, grab this one here, make sure we're doing it. So as long as we're not empty, that's fine. So if not self.is empty, we're going to say for position in, and then we want to do this recursive call here. So this is the recursive call, our subtree pre-order, given the self-root position. We're going to yield that position. I don't think we have the is empty, right? So our is empty, fine, is empty. We need, we're going to return self.data is not none. So if we have some data, right, we're not empty. Okay, so to do our pre-order traversal here then, this is our subtree pre-order traversal, given a position. First, we're going to yield the position. Right? I'll give you that position first. Then we're going to say for every child in self.children of the position, right? So for every child, we want to do this thing again, right? So for position in self.subtree pre-order, given the child, we're going to yield the position. Oh, I can't use position twice here. Shoot, this is child, I guess. Nope. I already have child. Subtree. Position. There we go. Why not? Subtree position. We'll yield that subtree position. So again, kind of think through this here. So we're going to start. Let's see if I can shrink that down so it makes sense. Maybe I can hide it. There we go. So if we have our tree here, right? 10. I should write the numbers first. There we go. So 10, 5, 20, 1, 100. There we go. I don't even need the circles, right? So we're going to go first. So the first position then is root. So we're going to start at root. Then we're going to recurse. We're going to do the subtree recursal thing. It gives the position back out. So we get our 10, and then it says for every child in 10. Right? So we're gonna call. I need children of 10. So first I'm going to get the right child. I get the 5 right child out first. I recursively call it. It yields itself. And then it says, okay, for every child of 5. So then I need child of 5. I don't have a left, so I get the right. I get the 1 back out. And then for every child, it doesn't have any children, so it's done. So this comes off the call stack. Now we're back at children of 10. It did the 5 already. Now we get the other child of 10, which is 20. So we get our 20 out. 20 gets its children out, and we get the 100 out. Ooh, that's a trippy view. A trippy view. So yield says, hey, give you back this thing, but wait. So our yield's the way that we can do iterators. So we can say, hey, if I have a bunch of items inside of me, I'm going to give you something and then wait for you to ask for the next one. So if we want to, then we can say for, I don't know what, item in binary tree dot preorder. We should be able to print item, or that's position, right? This is position. Position.data. Oh, binary tree has no object data. That's right. Oh, we have an is empty. Oh, it's self.root.data is not none. There we go. If our, oh, I guess we'll say if our root is not none, right? If we have a root, we're not empty. There we go. Uh-oh. We didn't actually give anything out. Preorder. If not is empty. Oh no, okay, so is none. So if root is none, then we are empty. I had that inverted here. Okay. Oh, we get a position. Oh, it's not data. It's data as a method here, right? There we go. So we get the 10, we get a 5, we get the 1, we get the 15, we get the 100. Okay, that's the pre-order traversal. Right? And in-order traversal, in order. Right, again, we're going to check if we're not empty. Do the same sort of thing here, but we want to do a subtree in order. In-order traversal. Okay, and then we need a subtree in order. Subtree in order for a position. So we don't yield the position first. Right? With the binary tree, we check, hey, if... I guess first we need the node. So a node is we validate the position. Self.validate the position. Position. And we say if node.leftChild is not none, we're going to yield self.inOrder subtree in order of that left child. So I need self.makePosition of node.leftChild. So, hey, the in order says, hey, visit the left child first. Visit the left child first. Visit the left child first. All the way left, 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 left. Once we've done that, then we give back the position, and then we give the right child. If right child is not none of the right child. That's the in-order traversal. So what the in-order traversal does, where's the whiteboard? Here it's going to go all the way left. Come on, whiteboard. Work with me. Come on. So instead of giving the node and then going to the children, which goes to the node and gives you the children, right, we get a, so if we had 10, 5, 15, this was a 1, and a 100, we're going to get all the way left first, and then the right child, and then we come back. So all the way left will give me the 5, and then its right child is 1, and then it's going to come back to the 10, because we did all the left children stuff first, then we get the 10, and then we start on the right, going all the way left, so then we get the 15 and the 100. So it doesn't look like it does a whole lot yet, but that's because our list isn't sorted. Once we sort our list here, it's going to make a lot more sense. So an in-order traversal. Yes, we should print, this is pre-order. And then we can print in order. Uh-oh. I broke it. Position, so in order is doing something wrong. So in order yields the position. Generator has no attribute data. Position, yield the position. Position. We yield the position. Position. Oh, that's right. So we don't even need to do, because we can get left and right. Yeah, of positions. We don't even need to do this node stuff. That's what. So if self dot left of the position is not none, do that. And then if right is not none, do right. Maybe that'll be a little cleaner here. No, still doesn't like it. Doesn't like my positions. So I make a position of left and right. Make position. Could give me back a none or could give me a position. I'm missing a yield. Where am I missing it? Let's see. Oh, that's right. We can't yield that directly. You have to say for what? For subtree. There we go. Subtree position. In order of self left of the position. I'm going to yield the subtree position. There we go. There we go. We can't give back the call here. We have to yield the item that results from that call. Self right. Okay. There we go. Okay, now this only works if we are actually putting things in order. So this should be, we should add left here. So we put our items in a binary tree in a particular order here. This is a, that's not a B, a binary search tree. Now binary search trees are fantastic. We love binary search trees. They're going to be really functional here. So the deal with the binary search tree is it's a tree, right? It's a tree here. It's a binary tree, so we only have a left and right. What makes it a search tree here is a rule. Okay, the rule says anything on your left has to be less than. Anything on the right has to be greater than. Okay, so this means no duplicates, no dupes. Right, so we're getting a set here, right? This is a set. Okay, because we can't have duplicates. So we're a set. The best text editor. So what that means then, if I want to go put something on the left, great, let's go add it on the left. Let's say, okay, let's add a particular value. So we'll add 5. So we have 10, we have 5. Now, it's recursive, right? So anything, everything. So I can't put something over here that is not less than 10. So it has to be like 7 and say 1, and this one could be, I don't know, like a 20. We could have a 15 and a 30 or something. Because that rule follows all the way down, right? Nothing on the right can be greater than you, or can be less than or equal to you, and nothing on the left can be greater than or equal to you, right? Everything on the left must be less than, everything on the right must be greater than, all the way down the tree recursively. Okay? So what this means then is I don't need to worry about how I'm adding particular left and rights. Right? I don't want to say, hey, add this to the left of a particular node. I just want to add it to a tree. Okay, and some of these traversals will make a little bit more sense. Let's run this. So what we can do then is we can have another class for binary search tree that extends my binary tree. Right? It is a binary tree. It does all the things binary tree does, but now we're going to be special. Okay? So when I add left and I add right, they don't need to give me all this position stuff. Right? Define init, get some data. Again, I guess that works the same way, that's fine. So we're just going to define a add right. We'll define an add. Add some data. So if you add data, we're going to go find out where we need to go put it. Right? So the rule is, if it's less than me, go left. If it's greater than me, go right. Right? So we need to see where is it greater than or left than, and we're going to go left and go right. So we can say if the data is less than self.roots.data, it needs to go left. We're going to do self.add left, right, of a position and the data. Sure, what's the position? Well, so left of self-root, and then the data is the data. And if the data is greater than the self.root.data, I think we can use that. And then we're going to add right. Of the root, we're going to add the data. Now what we want to do is we want to change the behavior of add left and add right. It's the position and the data. Right? So if we take a position, we need to go check. Right? We need to see, hey, if it's empty, great. If it's not empty, then we have a problem. Right? So we can say if, so we're adding to the left of this, so we need to validate. So the node is self.validate the position, and if the node's left child is none, good, we're good to add it. Right, no problem. We can call super add left. Given the position is position and the data. Which one? Yeah. All right, so if it's good, we'll add left using the super classes method add left. It's good to go. If it's not none, then we need to recurse. Right? We need to call self.addLeft of self.left of the position and the data. Right? If we had a left, so remember super goes to the super class. So that's the binary tree version here. So binary tree knows how to add something that's left. We can add left of a position. Okay, but the problem is I'm just telling, with a binary tree, you just tell me to add something, and I'm going to go find out, does it need to go left or right based on the greater than or less than. So if we do have a left child, great. If not, well, now it needs to go, oh, actually, we need to go add it to that particular position. Right, so if we went to add left and we had a left, now we need to see, oh, is it greater than or less than of that one, right? So before we do that then, actually we need to check, we need to get the, so if it is none, great, we add it, we're good to go. If it's not none, here we go, the else, if it's not none, we need to see, hey, are we going to go left of that one or right of that one? So the left child is no.leftChild. And if the data is less than the left child dot data, then we go add left of that one. Right? Else if the data is greater than the left child dot data, we're going to add to the right of our left child. The idea is if we have a tree here, right, we've got 10, 5, 20, 1, 7, 15, 30. If we wanted to add, say, a 9, right, we go to 10, we say, hey, I want to add a 9 to you, tree. Okay, well, it's less than that, so we go over here to this one. Hey, I want to add a 9 here. Well, we already have a child. Is 9 greater than or less than? Oh, it's greater than. Okay, so go to its right child. If it has a right child, all right, keep on asking. If it doesn't have one, throw it in there. 7, is it greater than or less than? It's greater, so we need to add a right child to 7 to add that 9 in here. Am I getting ahead of myself? I think I'm getting ahead of myself. Let me double check here. What do we have? I gotta check our schedule. I think I'm getting too excited with trees. Let me log into Canvas here real quick. And I still need to grade the midterms for you. I'm sorry, I'm behind on everything. Getting sick last week was no good. Let's see. The syllabus. Oh, it's right there in front of me. Yep, of course. Come on. Load, please. Come on. Okay, good. Oh, yeah, we did get into search trees later. Okay, so I don't even need to get into search trees. We have fall and winter are the main semesters, and then there's a summer semester. Because winter kind of goes into spring. Okay, so we can wait on search trees. We'll come back to search trees then. So this is just the general trees here then for adding left, adding right. That's okay. All right, so cool. We can wait on some of this then, but that's all right. So we want to add left, add right. I think we're about done. Let me just do the add right here then. And if it has no right child, I'm going to add right. I guess we can return that, right? Return. And these are the recursive calls. So then the right child and if it's, I guess we could just say child here. That's easier, right? I don't know. Hey, Blowfish, we're just about to wrap up here, actually. We're doing pretty good here on just generic trees. I got too excited and started doing a binary search tree, but that's okay. We'll come back to it. So if we're less than, we want to add left, and if we're greater than, we want to add right. But if we don't have one, great, we're good to go. So now let's see if we can do that. Let's see if that's enough. So let's make a binary search tree. Is our binary search tree given, say, 10, and then we should just be able to add a bunch of these values here. Right, we should just be able to call add, and all we want to do is add a bunch of things. So if we add a 5, and then bst.add a 20, what do we have here? And then a 15 and a 30, 15, and add 30. And then on the other side, we had a 5, a 7, a 1, and a 9. St, add a 1, 7, and a 9. And then what we want to do is we want to traverse it here. If we do an in-order traversal, now in-order makes a whole lot more sense here. Because what we're going to get is, oops, oh, bummer. Right child already exists. How do we not? We didn't check it. Something right here. Let's see. Oh, I didn't. I have to call it add right. Okay, we need to override. There we go. Now let's try that again. I call the method the right way to override that behavior. Oh boy. Okay. All right. Well, now we're failing. That's interesting. Yeah, when we added 9, add left of root and the data. Add left takes a position. It didn't validate the position. Shouldn't root be a position? We're getting so close, so close. Why is it not like, it doesn't like our position? Is it only the validating? Let's put it in debug mode. Let's see where it's breaking. We'll skip this one here. Let's see what we got. We can come back to our binary search trees though. I just was hoping this would work. Okay, let's step into add. So we're adding a 5, and our root's data is 10. So we are less than, so we're going to add left. Oh, definitely, we have to use the debugger. So we're going to make a position out of root, and we're going to add left. So root is our position, so we're going to validate that position as root. So self is the binary search tree, and the position then is a binary tree position. Is that the problem? Okay, if it's container is the binary search tree, and self is the binary search tree. Okay, we're good so far. So we validated root. Now, do we have a left child? So does that node have a left child? So node has no left child. Okay, it's none. So we're going to add a left position from add left and data. So let's step into, now we're in the parent class. Let's check our position here. So let's step into, we're validating. So let's check position. Is it position? Now the container, right? So the position's container is the binary search tree, and self is the binary search tree. We're good so far. So we validated the position. We're going to add left. If the left child is not none, we're okay. All right, so we make a node. We make position out of the node left child. So now node now has the left child. Right, now we have a left child with this 5. We're good so far. We returned. Okay, so we added 5. Oh, that was good. All right, so now we're adding 20. Okay, we're not less than. Are we greater than? Yep, we're greater than. Okay, good. So we're going to add right of root. Makes a root. Makes a position. Now we're adding right. Okay, so we're adding right in binary search tree. If the right child is none, we can add none. Great, so we're good to go. So let's add a right child. We validate. It's not none. We'll make a position. We return it. We added right. We're good. Okay, so we did 20. Now we're on 15. Okay, now we're going to start testing our recursion. Pen and paper debugging or printing? Oof. Yeah, I mean, being able to do it by pen and paper is good. So we're trying to add 15. So 15 shouldn't be less than. 15 is greater than. Good. Let's step into. We're going to add right of root. We're good. Keep going. We're adding right. Okay, so now position. We're going to validate the node. Node has a right child already. So right child is not none. We're going to go to our else. Okay, now we need to check. Hey, is it greater than or less than? Well, is 15, here's our data, is that less than the 20? Yes, it is. So if it's less than, we need to add it as a left. So left of the position. Okay, so let's step into, we're going to make a position out of left, out of the left child. Step into, so now we're adding left here. So the position, right, that node we're trying to add to the left of now is 5. Is that right? 5. Adding left. Trying to add a 15 here. select the position. Oh, did I give the wrong? I gave the wrong child here, didn't I? Yes. Okay. So if we're less than, we add left. If we're greater than, add to the right. Both of these need to be right. That's the problem. Right position and right position. Oops. Right and right. Okay. There we go. Okay, that was the problem. So when we are on the left, we need to get the left ones. We're on the right, we need to get the right ones. Maybe that'll work now. That was the problem. Let's give that a run. Hey, all right, and then we get out our binary search tree in order. Right, all that fun stuff here. Okay. So that's with a positional binary tree, or a binary search tree. Again, just let's do a little bit of extra fun stuff here. So our positional tree, let's commit this one here. Come on, wake up, GitHub. This is a binary linked tree with linked nodes. Okay, so what do we have? So next week we have priority queues. Oh, priority queues are really fun. And then we'll look at maps, hash tables, and skip lists, and then we'll get to search trees, sorting and selection. We're cruising along. So we'll have another lab on trees. We'll finish up doing a couple of things we need to do with the binary tree, just the generic binary tree, ways of two trees interacting, being able to add one tree to another tree, right? Add it as a left tree or a right tree. So we'll take a look at that for the lab. I'll post a quiz for chapter 8 for the trees chapter, and I'll work on getting your stuff graded. Yeah, we'll make our own priority queue. Yep. Yeah, priority queues are awesome. The min queue or max queue. So we'll get there, okay? All right, hopefully the binary tree is a little bit more basic, a little bit easier to wrap our head around. Again, the entry is cool and all, but probably trying to do that iteration stuff over it was just a pain. And the traversals don't make a whole lot of sense yet. So we can look at some of them too. There's a breadth first and a depth first traversal, which is fun. We can use a queue for a breadth first traversal instead of a depth first. All the ones we did were depth first because we went all the way left and all the way right first. Right, where we went down. So a breadth first traversal does everything at every level. So it does everything at height 0, everything at height 1, everything at height 2, which is fun. So we can look at that as well. Maybe we'll do one of those in lab. All right, it's been fun. The next project, shoot. Yeah, let's talk about the last project here. Pull up this here. Let me get it here. That's right, our last project, and then this will be our last individual project. I was hoping to have one more, but that's okay. I don't want to push too much on. I know the semester's been crazy already. So we'll do, this one will be, it's using linked objects, not a linked list. So it's really fun. So the idea is we're going to have these links together in our objects, right? But they're not going to be a linked list. Right, the linked list is a generic that can store anything. For us, this is going to be just the object itself has a link to the next object itself. Okay, if that makes any sense. So let me start up a new project here. 3 linked objects. Oh, this is, I don't know, we'll call it binomial linked objects. Right, and this one's worth, let's see, let's do, you know what, we can put this one out till April 1st. I think that'll be fine, so we get a little bit of extra time on it. Nope. April 1st, 2021, 3:30 p.m. Okay, and this will be worth 20 points. Okay, pull this open here. Give me a second. There it goes. All right. see if I can get this to actually copy here. Sorry, right? Copy paste just never likes to work for some reason off of here. Okay. So we're going to write a polynomial helper. We're going to be able to add polynomials, multiply polynomials, differentiate polynomials, and integrate polynomials. It's a list of term nodes here. So the class term node, right, has an exponent and a coefficient and a next. It might be none. It might not be. So a monomial, right, has no next. Binomial has one next, right, and on and on. And we just link those together. Right? You should be able to tell whether or not one term is equal or not equal. And then polynomial here has a first node. You can initiate and instantiate a polynomial with the exponent and coefficient. It makes the first term node with that exponent and coefficient. You should be able to add one polynomial to another. You should be able to multiply a polynomial with another, differentiate a polynomial, integrate a polynomial. Just assume your constant 0, right? We don't worry about any of that stuff here. We want to be able to do a string representation of our polynomial. So in descending exponential order, and anything x to the 0, we should clean up, right? You're just a coefficient at that point, right? If x to the 0, you're just your coefficient. You're going to round your coefficients to 2 decimal places. You're supposed to check if one polynomial equals another, and if one polynomial does not equal the other. Okay? So what we can do then with these, right, sort of some examples is, say, okay, if I make a polynomial with 2, 3, I've got 2x to the third. If I make a polynomial 3, 4, I get 3x to the fourth. If I take poly 1 plus poly 2, my poly 1 should be 3x to the fourth plus 2x to the third, right? This descending order, exponential order, right? Higher exponents first. Right, I can print it out. Poly 3 is poly 2 times poly 1. Right? Remember when you multiply polynomials, we're just foiling. We also need to make sure we're combining like, exponents. Right? If we differentiate, remember we take the power down by 1, multiply the coefficient by the previous power. Right? And integrate is the opposite. Right? So if we're taking poly 1 and integrating it, so poly 1 was 3x to the fourth plus 2x to the third. Okay, so we do the opposite. So we increase our exponent, and then we divide by. Right, so 3 divided by 5, 0.6. Right, 2 divided by 4 is half. Okay, and along with unit tests. So it's 20 points. So you're going to submit the, no, not paper, online website. You do this one, and then I'll add a rubric for it real quick here for you. This is the project 3. This is the term node class. This one's 3 points, right, for the term node. And then our polynomial add, right? If add works, right, there's 3 points. Polynomial multiply. Remember, we're overriding these behaviors, so we can multiply those together. Multiply is 3 points. Okay. Polynomial differentiate, 3 points. Polynomial integrate, 3 points. Polynomial string, it's 3 points. And the last one, equals or not equals. Polynomial equals and not equals. That one's only 2 points, right? 1 for each. Okay, so we got the rubric here. Again, the term node is the linked class, so it has its next here, right? And we add and multiply these things together. Note about adding and multiplying things, right? So think back to math class, right? Let's find some space over here. Whoa, okay, sure. So 3x to the fourth plus 2x to the seventh. Does your result change this one or change this one? No, no, neither of these things change, right? So if this is P1 and this is P2, they don't change, right? We get a new result back. So when you add together, you get a new result back. When you multiply, you get a new result back. When you integrate, you get a new result back. When you differentiate, you get a new result back. So don't change the original, right? Don't change the originals, just make a new polynomial with the result. So everything is a new polynomial. Let me add that in here, right? So, come on, Canvas, don't be so slow. Come on. Maybe. There we go. Okay. So remember, the originals don't change. You create a new polynomial result. Right, this idea, so it returns a polynomial. It's a new polynomial. So if you add another polynomial, I'm not changing the original, I'm not changing the other one, I'm giving you back a new result every time, okay? That's kind of the goal there. Right, so unit testing to make sure it works. Right, that's you get your points are kind of baked in, so add plus unit tests there for the full points. If you're missing unit tests, you lose a point out. Okay? Any questions, thoughts, concerns? If not, we'll call this good. We'll have a lab on Monday, working more on trees, playing with our binary trees, doing a couple more operations on those, and we can go from there. All right, folks, that was fun. Let's see if anyone else is around on Twitch. It's a little better than Tuesday. Not too much flog. I'm trying to work through some of those annoying code issues. Let's see who's around. Who's going to watch some chess? Let's go see if we can watch some chess. I don't actually know if we can raid their channel. We'll see if we can or not, just for fun. Why not, right? Hey, it looks like it's going to work. All right, folks, go have fun. My friends, the Chess Bras, and I'll see you around. You guys take care.